And now when I went through that process of algebraic substitution and the substitution model with that simple example, there's a reason I did that, and that's because that's exactly what we're going to do with our word count code in this next lesson. So as I note right away here in this line right here, because I wrote word count using only pure functions and immutable values, or immutable variables, I should say, both you and the compiler are free to reduce the code exactly as I just did in that simple example. And now I'm going to take just a few minutes to walk through that. The first thing I want to note is this quote, and I got it from this book called Land of Lisp. And the second paragraph is the most important right here. And it states that in the lambda calculus, you run a program by performing substitution rules on the starting program to determine the results of a function. And here's where it gets interesting. It says the result of a set of functions just sort of magically appears by performing substitutions. And he furthermore notes that functions don't really return values. And therefore, he sums it up this way, and he says, because of this, Lisp purists prefer to say that a function evaluates to a result. And that's because we go through the substitution process that he mentions right here. Everything is just kind of substituted, and then everything evaluates to a result at the end. And that's what I want to show first here. So let's take a look at that. So to set this up, I have two functions up here. So sum is a function that returns the sum of the two integer values that it's given. And then times is a function that multiplies the two values that it's given. So these are a couple of simple functions that we can work with, and they will actually demonstrate this very well. And I'll start by saying val a equals, let's say, the sum of 1 plus 1. And then we'll create another variable, b, and we'll say that one is the sum of 2 plus 2. And then finally, c equals times of a and b. So we're going to multiply whatever a and b are. And now we can start looking at this substitution process. So an interesting thing here is because sum up here is a pure function, it just has two variables coming in the front door and it returns an int. And then this is just a pure mathematical algorithm right here. Sum is a pure function. So always and forever, anywhere inside of our application, even if things are multi-threaded, a right here will always be equal to the sum of 1 plus 1. And so what that means for our purposes is that we could take a and replace that with the sum of 1 plus 1 right there. And this is something we can do, and it's also something the compiler can do. And this statement is so important, I want to include it right there as a comment. So again, a and the sum of 1 plus 1 are always and forever equal anywhere in your application. And again, even if your application is multi-threaded, that is true. That's a true statement, and that's because sum is a pure function, and a is an immutable variable. And now our second substitution, come down here. This one we can replace b with the sum of 2 plus 2. So that's another step. And I may not have mentioned this clearly enough, but this process is called algebraic substitution. That's one term you can look up. And this part that I'm going through right now is also referred to as the substitution model. So all I'm doing is replacing my immutable variables with their equivalent relation right here. And now we can keep going through this process. And if you think about that quote that I shared earlier, what I'm doing now is actually just reducing the code. So we and the compiler both know that this expression right here, this function call, is exactly equal to the addition of these two variables right there. So that's actually equal to, let me do it this way just to be clear, that that's equal to 1 plus 1. So we can substitute that right there. And then similarly, when we go in the next step here, we can say, well, that's again exactly equal to that. So this is the sum of 2 plus 2. And now we keep reducing the code. So again, going back to that quote, this is exactly what the compiler is doing, and exactly what we can do. And the steps here could vary. I could have done the other part first, but what I'm going to do right here is say, well, let's just stop right there and say that now we can replace times. So again, times is a pure function. We look up here, and times multiplies the two values that it's given. So that's what's going on here. So now we can get rid of times and replace that with this. And let me just scroll up a bit there. And then, of course, in the last step, we have val c equal to 8. So you can think about almost all of this really being the substitution model or algebraic substitution. So just as a quick little summary, I started with the immutable variable c being equal to this function call right here. That was the first step. And then we could start applying the substitution model. And here I substituted the sum of 1 plus 1 for a. Here I substituted the sum of 2 plus 2 for b. And then I just kept reducing this algebraically and went through all these steps. So all of this part here down to here was just algebraic reduction, more or less. So coming back to this quote real quick, I didn't mention it before, but the lambda calculus is a way of referring to functional programming. And he notes that you run a program by performing substitution rules on the program, and then the result of a set of functions or a set of function calls or pure expressions that we just created, this result just sort of magically appears by performing these substitutions. So again, we say that the equations that we created evaluate to a result. And that's exactly what I did in the code over here. So let me slide that down here. And that's exactly what we did over here. We performed all these substitutions for these variables over on the right side. And then our solution just kind of magically appears right here at the end, just by going through this substitution or reduction process. And next, I want to be 1,000% clear about this part right here, where I say that a and the sum of 1 plus 1 are always and forever equal anywhere in your application, and the fact that that is only true because sum and times are pure functions, and because these variables over here are immutable. So let's take a look at that. One way I can demonstrate this is by having sum refer to some global variable. And worse than that, it will be a mutable global variable that I'm going to create with the var keyword. So let's say var g currently equals 42. At some point in the application later on, g may be equal to 0 or maybe equal to something else. But when it first starts up here, g is equal to 42. So let's look at how this might possibly work. Let's try to do reduction right here. So a is equal to the sum of 1 plus 1. That's what we had before. And now if I try to include that here through reduction, we have that. But let's do this a little bit differently. Let's make this stand out a bit more. Let's say we have C at that point. Now we have D. So for some reason, we're calling that again. And the problem is that somebody reset G right there. So here, earlier on, we said that, well, C could be equal to the sum of 1 plus 1 always and forever. And then if we try to do that same reduction down here and say, well, of course, that's equal to the sum of 1 plus 1. The problem is that G was just mutated right here. So where A and the sum of 1 plus 1 were always and forever equal anywhere in our application, when sum is a pure function and A is immutable, we no longer have that case down here. And in fact, what you'd get up here is that this one would be equal to, oh, what's the sum of 1 plus 1 is 2 plus 42 would be 44. And then this one would have been equal to 2. So we can't do that same substitution that we did before because A and the sum of 1 plus 1 are not equal always and forever anywhere in our application. This starts to break down. And you can imagine that if this was a multi-threaded application, how much worse this situation would be. Because you might have this expression up here, and then anywhere down in your code later on, you might have a reference to A here, and then you could have, val E equals some other reference to, I don't know, let's say you wanted to sum A and A or A and B or something like that. What's happening is A keeps changing over time. So at the start of your program, A might be 44 here, and it might be 44 here. So you'd get the sum of 44 and 44 in this situation. But if E was somewhere lower, or again, this was a multi-threaded application, and G was changed to something else, this can't be true. And what I'm getting at is the compiler cannot reduce your code, and you cannot perform algebraic substitution to think about your application, because A and the sum of 1 plus 1 are not always equal. So that's one possible example. And another one here is going to be a bit different. So here I change sum so that it prompts somebody and says, please enter an int. Then it reads the int, and then it adds that int right here to the sum of I and j. And we call this one a side effect. And even though here I'm prompting a user for input, you could think of this as being a database call or a web service or anything else where you get the information from the outside world. And the problem with this, again, is that this value is always going to be different, or very often it's going to be different. So then I could go through the exact same steps here if you wanted to, and that is that A cannot be replaced by the sum of 1 plus 1. You and the compiler cannot do that when they look at your code. And again, if you were to keep going through more and more examples, then this could not be true later on, because what happens up here is this is going to happen right here. We're going to get that outside value. So A is going to have some value here. And then when sum is called sometime later here, it's going to have a different value. And when it's called here, you're going to again have different values. So again, you cannot apply algebraic substitution to this type of code. And actually, it's even a little bit worse, because read int can throw an exception. And I could show that right here. So we say val res equal that. So right now it's waiting for me to type in a value. So if I type in 42, you get 42. But if I do that again and I say hi mom here, now we get an exception, the Java lang number format exception. So then this particular code is impure in two different ways. First, it's reaching out into the outside world to get a value. And second, it can possibly throw an exception. So you could never do the algebraic substitution that I'm trying to show here. So again, I'm trying to show this one fails because it's an impure function. This one fails because it's also an impure function, because it refers to a mutable variable somewhere in the global scope. And because I'm talking about mutable variables, let me just say one more thing, that if I had made a mutable right there, then that would be even worse, because then you could sometime later in your code just say, well, a equals 65, and then all bets are off, right? And in summary, I want to come back and look at this code and say that I was talking about algebraic substitution and the substitution model. And I showed this code with the pure functions, immutable variables here. And then we went through the substitution process all the way here. And then I demonstrated that this only works when the functions are pure and the variables are immutable. Next, let's see how algebraic substitution works with the word count example. And the key here is, because I wrote word count using only pure functions and immutable values, both you and the compiler are free to reduce the code. So what this means is that when I first sketched out all these functions, what I could do is, we had this function, and now I can go back and look at this initial map variable, and I can see that, it's up here. And what happens is that initial map is exactly equal to this, and it always will be, because the values are immutable and the functions are pure, as I note there. So what I can do is take this initial map right here and replace it with this function call right here. And that's what I do on the next page. And that's what I continue to do on the next several pages. So let's go back over to the code and actually try that for just a few moments. So let me move that over here and do that over here. So I was working with initial map right here. So initial map is exactly equal to this function call right here. And it always and forever will be. So what I can do is I can get rid of that initial map temporary variable. And just to make things easier, what I'm going to do is start formatting this like this. And then next thing you can look at is, well, this lowercase list of words is always and forever going to be exactly equal to this function call. So I can get rid of that temporary variable. And then with another formatting change, come down there and do that. Now we have list of words. Well, list of words is always and forever going to be equal to that. So we delete that and so on. So I sped that up so you didn't have to see me type all that, but what I did was I just replaced all those temporary variables with their exact equivalent function calls. And again, that only works because these are pure functions and each value was immutable, and you didn't have to worry about it being mutated sometime later. So now we have this sorted map variable right here, and indeed we can get rid of that one as well. So I come back here and delete that guy and delete that right there. And now we actually have the new solution. And I hope you'll agree this is still fairly easy to read. As long as these names are meaningful, I hope this is still fairly easy to read. And it's kind of funny to me because whenever I do this, my code looks like Lisp, the programming language Lisp, L-I-S-P, because what you do is you read it from the inside out. So you say, well, what's going on is word count receives this document right here, and then that document is passed into this function. It replaces those new lines with blanks. That result is then passed here. That result is then passed here, and so on. So you're actually working from the inside out. So if you like this Lisp style, this is one way to write your code like this. And if you don't, then you can just undo everything I just did and have all that expression-oriented code that I showed earlier. But what I'm trying to show here is algebraic substitution, and it works in both ways. So what I just did was replace immutable variables with their equivalent function calls, but you could also do the opposite if you wanted to. In other situations, you could replace function calls with variables. And so I could do that, like if I wanted to unwind this code, that's exactly what I would do. But for right now, I'm just going to leave this solution like this. And again, this is called algebraic substitution, this whole process that I just did. And it works only because the functions are pure, the variables are immutable, and the data structures are immutable. And when code is written like this, both you and the compiler are perfectly free to write it in either of these ways. It's equivalent both ways. But if you use mutable variables, mutable data structures, or impure functions, the same thing cannot be said. You cannot do this algebraic substitution.